Reversible rates and equilibrium. Most reactions do not go to completion. They are reversible, which means reactants form products, but products also form reactants. So let's look at this example. The forward reaction, H2 plus I2 forms 2HI, and the reverse reaction is 2HI decomposes into H2 and I2. What we can do, instead of writing two equations, the forward and reverse, combine those into one and use a double-sided arrow like this to show that a reaction is reversible. So let's look at this equation a little bit more. H2 plus I2 forms 2HI. Initially, there's no product present. There's no HI present. So the reverse reaction is 0. But as we form HI, the decomposition begins and the rate of the reverse picks up. Similarly, the rate of the forward slows down, and eventually the two rates become equal. So the forward rate, the production of 2HI, is equal to the reverse rate, the production of H2 plus I2. And we are in a state of chemical equilibrium, which is where the forward and reverse rates are equal and no net change occurs in the amounts of the reactants and products. At chemical equilibrium, the forward and reverse reactions do not stop. We are still producing product, we are still producing reactant. But because the rates are equal, no net change occurs in the concentrations of reactants and products. Now the rates may be equal, but the concentrations on both sides of the equation are not necessarily the same. So you don't have to have 50% reactants and 50% products at equilibrium. We're going to look at something called the equilibrium position, which indicates whether reactants or products are favored in a reaction. For example, let's say we have this reaction, acetic acid reacting with water. It's going to produce H3O plus and acetates. The longer arrow indicates the favored direction. In this reaction, the longer arrow points toward reactants, so reactants are favored at equilibrium. Let's just put some numbers here. At equilibrium, it's possible to have 98% reactants and only 2% products if reactants are favored. Almost all reactions are reversible to some extent. So again, we're going to use the double-sided arrow, but if you see different lengths of the arrows, that's going to indicate what's favored at equilibrium, whether it's reactants or products. Catalysts speed up reactions. They speed up both the forward and reverse reactions, so they don't affect the equilibrium position. They don't affect the amounts of reactants and products present at equilibrium. Let's look at Le Chatelier's principle. When an equilibrium is disturbed, the system makes adjustments to restore equilibrium. And the restored equilibrium is often different from the original, so it's called a shift in the equilibrium position. So Le Chatelier's principle says that when a stress is applied to a system, the system will act in a way to relieve that stress. There are three stressors: concentration, temperature, and pressure. Let's look at concentration first. Let's consider this reaction. It's at equilibrium. The decomposition of H2CO3 is at equilibrium. Let's say I add more CO2. That increases the concentration of the products because CO2 is a product. It's going to cause the rate of the reverse reaction to increase, and that's going to cause more reactants to form. So once equilibrium is reestablished, you will have a higher concentration of reactants. So we say if I add CO2, the equilibrium position shifts left. It shifts toward reactants. I produce more reactants. Here's the short rules for that. If you add something, it shifts opposite every time. If you remove something, it shifts in the same direction. So those are my rules for concentration. So let's look at further examples with the same reaction. Let's say we're at equilibrium, but I remove CO2. Well, if you go back to the equation, CO2 is a product. If I remove something, it shifts in the same direction. So if I remove a product, it shifts toward products. You just draw an arrow to the right. Let's say I add H2CO3. Well, H2CO3, go back to the equation, is a reactant. If I add something, it shifts opposite. Opposite of reactants is products. So we just draw arrows to say which way the equilibrium position will shift. It can be left, it can be right, it can be neither. So these are the rules for concentration. Add shifts opposite, remove shifts the same. Okay, temperature. Temperature can affect the equilibrium position. I like to consider heat as a reactant or product. So in this example right here, you'll notice heat is a product. So it's an exothermic reaction. If I increase the temperature of this system that's at equilibrium, I'm increasing a product. If you increase, it shifts opposite. So if I increase a product temperature, it would shift opposite, which would be left. Okay, let's say we've reestablished equilibrium, and now I decrease the temperature. So the heat goes down. If you remove heat, it shifts in the same direction. Heat is a product, it's going to shift toward products. So temperature and concentration, practically the same concept. If you add, it shifts opposite, remove, it shifts the same. Now pressure only affects gases. If I change the pressure, it's only going to affect gases. An increase in pressure favors the smaller number of gases. So let's look at this example. If you look at this example and we look at the moles of gas, I have 1 N2 plus 3 H2. So I have 4 moles of gas on the left side, on the reactant side. On the product side, I have 2 moles of gas. If I increase pressure, it's going to go to the smaller number of moles. So if I increase pressure, the equilibrium would shift right. If I decrease pressure to a system that is at equilibrium, it's going to shift to the higher number, which is left. Okay, let's look at this example right here. How is the equilibrium position of the reaction affected by the following changes? We're at equilibrium. Letter A, we lower the temperature. Temperature is heat. Heat's right here. It's a reactant. If I remove a reactant, it's going to shift in the same direction. So lowering the temperature is going to shift left toward reactants. If I remove something, it shifts the same direction. Increasing the pressure. Pressure only affects gases. On the left side, I have 1 mole of gas, and that's H2O. On the right side, I have 2 moles of gas. If I increase the pressure, it's going to go to the smaller number of moles, which is toward the reactants, just left. Removing hydrogen. Okay, we're at equilibrium again. We remove hydrogen. If I remove something, it shifts in the same direction. Hydrogen is a product, so it's going to shift toward products. And then finally, I'm at equilibrium and I add water vapor. I add H2O. If you add something, it shifts opposite. Water is a reactant, so it's going to shift toward products. So that is Le Chatelier's principle. How does a system respond when stressors are added? Concentration, temperature, or pressure changes. How does that system respond?